Alright, we move to the next chapter. Next chapter is chapter 15. So we're gonna jump a little bit. We will come back, but I think that make good flow of the material. Nuclear energy. Alright. This is the what is the marking? Nuclear reactor in the USA. And we are the largest country in the world to use nuclear energy, followed by France and then Japan. Okay. So we're gonna talk about where this energy is coming from, how we can calculate it, and we will talk about the safety of this nuclear reactor, because that is main concern. Basically, whenever you talk about nuclear energy, people don't feel safe about it. So we will find out whether they are right, public is right in being scared, or no, they are not. Okay, we'll find out. So where this energy is coming from? It's coming from the change in the mass. Okay, so there is this famous equation that basically say E equal mc squared, delta mc squared. So delta E is delta mc squared, meaning that if the mass disappear, you will get energy. And the relation between them, between the kilogram that will disappear and the joule that will come out, is the c. The c is the speed of light, the speed of light, c squared. So that is a big number. 300,000 kilometers, right? So it's like 300 times 8 to 10 power 8, basically. It's like really huge number. And it's square. So then you don't need that much mass to disappear. Now, so first of all, we need to learn to calculate the mass. So most of the mass is inside the nucleus. And you can see the inside nucleus there is neutrons and proton. Neutron are neutral, no charge. Proton as positive. And electron are negatively charged. The mass of the electrons is nothing compared to the mass of the neutron and the proton. And the mass of the proton and the neutron proton are almost one atomic mass unit. What's atomic mass unit? This much kilogram. Okay, 1.66 10 to minus 27 kilogram. So the majority of the mass is in here. And because of this, when they do the nuclear reaction equation, they don't care about the electrons. It's not important how many electrons are there. They just care about what's inside here. Of course, in chemical reaction, the electrons is a big deal, because that's how the bonds is made and how things are reacting with each other, and right? Very good. So we care about what's inside the nucleus. And so the number of protons determine the positive charge and determine the element. So if you have one proton, then you are hydrogen. Done. Hydrogen. Now the number of neutrons that you add does not change the positive charge and does not change the element. If you have one positive charge inside, one proton, you are hydrogen, you are done. Okay, now whether you have one more neutron or not, that basically make the element a little bit heavier, and it's called isotope of hydrogen, but he's still hydrogen. He's not going to change his name. So what determines him, whether he's hydrogen or oxygen or silicon, is or uranium, is the number of positive charge inside. Okay, very good. So that's what I say over here. The number of protons is called atomic number, and it's written over here, and that's what will determine what this thing is. Okay, so if I have one, that's H, and therefore sometimes people don't really write one H, they just know it's H, then it has to be one. Uranium, for example, 93, people don't have to write the number 92. Or helium has 2 protons, so you don't have to write 2He4. It's enough that you write helium, then you know it's 2. It will not be, there is no helium without this 2. But the number on the top, what is that number on the top? That is the mass number. That is the total number of neutrons and protons. And that could be different. So you can have one H1 or one H2. It's still H, still hydrogen, but this guy is a little bit heavier than this guy. Okay, or you can have 1H3. So those are all isotope of hydrogen, heavier and heavier hydrogen. Okay. So in some of the problems, basically, you will calculate how many protons and how many total inside here, and then you will be required to figure out what is the element that we are getting from this reaction. So how do you do this? You go to the periodic table over here, and you will basically find out. So here's uranium is 92, right? And if you see 92, you'd say, well, this is uranium, and then that's all you need to figure out uranium. The number on the top is just basically how heavy that uranium is. Okay, and there is a bunch of isotope for every element we got. Right? So if you open the periodic table, this is a symbol of the element. The number on top is the number of proton. The number over here is the number of the atomic mass, the total number. And you see, what is this fraction? What do you mean 20.1797? Well, there is a lot of isotope, and that's the average. Right? Now, this numbers over here, the 2 and 5, or 2, 3, 13, and what is this number? What are those numbers in the periodic table next to the element? This is xenon, for example. They use xenon for rocket engine, the electrons, right? The electron different shells. So KLMNO, basically at different shells, they are basically telling you you'll have 2, and then you have 8 over here, and then 18, and then 18, 13, and then 8. Okay? So looking at this, you can tell what is the element by the number of proton and what's the total atomic mass. Okay? So again, we'll look at the equation, calculate those guys, and then come to the table and figure out what is the element that we are generating. So those isotope, again, how many total particle we have inside the nuclei. Some of those isotope exist only for very short time. So basically, what does this mean? You can generate them in the lab, like you put an extra neutron in, or you do chemical reaction, and that basically isotope show up, but because he's unstable, he kick a proton or neutron, and he basically transform to something else. And those become basically, like people use them for a lot of medical application. You just need this particular unstable element for diagnostics, so that they can bind to a cancer cell or something, and then you can tell where it is, or use it for curing someone, because the radiation is important to kill something in your body. And some of those isotopes are totally stable, meaning that they exist in real life and they stay for forever, or stay for a really long number of hours. Okay? And here are some examples of the stable or unstable isotopes. So the guy that we care about the most is uranium. Okay? And 92 uranium. So again, we don't have to write 92. Just the fact that we write uranium is enough for us to understand that it is 92. So this guy has a lot of isotope. Okay? So you got 238, 235, 234. So he got basically 14 isotope, all the way from 227 to 240. All of them has 92 what? Yes, protons. All of them has 92 protons. Now, the majority of uranium in the world is 99% of the uranium in the world is 238. Only 0.7% is 235. Okay? Now, this is really unfortunate, because guess which one we need for our nuclear reactor? we need the 235. Okay, so we need the one that only exists at 7.7% in the world, and the rest of the uranium, the 99%, is basically not really useful for regular reactors. Huh? No, it just for, we will see how we can generate energy from it, but it's not useful for regular reactors. Okay, it's not useful for regular reactors. So we need, unfortunately, we need only this 235 guy. Okay, so now how do they, first of all, how does nuclear reaction happens? So in chemical reactions, when we react carbon with hydrogen to make CH4, or burn oxygen, C plus burn carbon with O, C plus O2 becomes CO2, we always keep the same number of atoms between the input and the output. So if you have one carbon atom in, you will have to have one carbon atom out. If you have two H2N, you bet you will have H4 out. Why? Because in chemical reactions, the number of atoms are conserved. They don't change. Okay? But in nuclear reaction, the number of the species are not conserved. You could start with uranium N, and you don't have uranium on the other side. You could end up with carbon N, and on the other side you end up having basically nitrogen. How come? Because they, in nuclear reaction, they start losing or gaining neutron and protons. And when they do this, the element change. Right? So if you use a positive charge from inside you, your proton become a neutron. And suddenly, rather than 92, you become 91. You just lost your charge. Huh? So you become another element. So in nuclear reaction, you can have whatever K and L, whatever this K, L, and you end up with M and N. But what is conserved in nuclear reaction is, and this is how we can do the equations. What's conserved is, what do you think is conserved? Not the actual species, but the charge. So the number of positive charge, or the number of basically proton in and output, they should be the same. And the total number over here of neutron will be the same. So the total number of particles remain the same. But the elements lose to each other. Okay? And what is amazing for the first time, so this is what this thing is saying to you. So Z1 plus Z2 has to be equal to Z3 plus Z4. Number of positive charge need to be the same, and A1 plus A2 should be equal to A3 plus A4. Those are the same. You end up with the same number of neutron, the same number of total particles. Okay? So here's an example. We say this reaction, aluminum and helium reacting with each other, and you end up with silicon. And what? Calculate for us what's happening over here, and what is the, so how are we going to calculate this? What's the rule? The 13 plus 2 need to be 13 plus 2 over here. So this is 15, I better have 15. So I got 14, then this must be 1. So 1 over here, which is hydrogen, right? And on top I have 27 plus 4, that is what, 31? And I end up with 30, this must be 1. So this is 1 and 1. I open the periodic table, and what's 1 plus 1? That's hydrogen. And I tell him hydrogen. Okay, that's how we're going to do those problems. Okay? So he's basically saying X, whatever that X is. It doesn't mean xenon, XE, just saying X. And he calculates those two numbers, 1 and 1, and figure, it must be 1 and 1, that's hydrogen. Now what is amazing, and this is happening for the first time of your life as a mechanical engineer, is mass of the reactant is not the same as the mass of the product. So I build my career in fluid mechanics saying in every single fluid mechanics lecture, mass is conserved, mass is conserved. M dot N equal M dot out. For the first time, M dot N is not equal M dot out. Okay? So now, why is that? I don't know. I need another life where I become a nuclear engineer and study nuclear engineering, so I can tell you why does the mass disappear in nuclear reaction. But what I can tell you is that you don't really know what mass is. Like we think we know what's a mass, but what is a mass? Because the atom is almost empty. Like what is mass? What makes something worth 1 kilogram? What is it that make a mass? And I'm talking about particle physics, like inside what is mass really? So if we understand what is mass, we will understand why does mass disappear in nuclear reaction. Okay? I really wanted to be a nuclear engineer, but my family didn't approve because it was in another city, and although my uncle lived in that city, they said, no, you're not going to go there, you stay here. So, but I really wanted to become a nuclear engineer. Anyway, so until we figured that problem, like why does mass disappear, let's just use it as mechanical engineer. So as a mechanical engineer, we care about, let's calculate the mass at the right hand side, mass at the left hand side. Take the difference, and when we calculate the difference, it is minus 0.00254. That number multiplied by c square is going to be the energy released from this reaction. Okay? Make sense? So m multiply delta m multiplied by c square is going to be the energy that will be released. Okay, so now when we do this reaction, you will not always end up with, you know, hydrogen or helium. Sometimes you end up with weird combination. You will end up with -1 and 0. What is -1 and 0? What have 0 mass and negative charge? Electron, right? So if you end up with -1 and 0, you just emitted an electron. And if you end up with +1 and 0, what is that? That is, no, proton is 1 and 1. No, it's not. It is the opposite of electron. It's positron. So a positron is positively charged electron. Okay? And there is like 0 and 0, which is like neutrino.